Okay, so today we're going to talk about Chapter 10A. This is points, lines, and planes. So this is basically, there's a little bit of work to do in this section, but the most thing about, or what you'll see most of in this section is kind of like definitions, things to explain what they are, what's the very, particular definition of, like a point, line, plane, so on and so on. So yeah, just please take notes on this. There's kind of just a lot of information, not so much a bunch of work. So let's just get started. So this section is going to be talking mainly about points, lines, and planes. Okay, so a geometric point is imagined to have zero size. So when you draw a point like this over here, the point in size is more just for us. So like you see here, how this point is like that. What if I, shaded it in even bigger? That doesn't make a difference. They're saying we think of it as being infinitely small. It doesn't actually carry a width. It doesn't actually have a size to it. It's more of a location. A geometric line is formed by connecting 2 points along the shortest possible path. And once again, this is a line, and then this is a line segment. Okay, so just keep that in mind. Let me draw that out here. So this is a line, right? But when they talk about line segment, so let's say you have a line like this, okay? Then if you want to chop off, like say from here to here, and you do from there to there, and then you connect the dots, you connect the points, this is a line segment, and this is just a line. So lines go on for infinity in both directions in mathematics. Line segments, are pieces of a line, from a starting point to an ending point. Okay. A geometric plane is perfectly flat surface that has infinite length and width, but no thickness. So once again, think of a sheet of paper, but it's even thinner than a sheet of paper. And think of a sheet of paper that goes on forever in every direction. So that's what a plane is. Okay. Dimensions. The dimensions of an object can be thought of as a number of independent directions in which you could move if you were on the object. So we can also think about dimensions by the number of coordinates required to locate it. So try to imagine if you're drawing something on the XY plane, right? So, I'll use their pictures. So what they're saying right here is imagine you have this point 3. That is a one-dimensional idea, okay? So it's just that one spot, okay? 2 coordinates locate a point on a plane, okay? And then 3 coordinates locate a point in space. So think of like a classroom or something like that. Imagine if I drew something on the board, or if I drew it on the screen. Let's say we have this point here, let's say we come here, right? So, and then now imagine that it comes out. So it's I'm trying to use my hand to show it, but imagine that it comes out from the screen. Okay, so that's a third dimension that you have to worry about in terms of finding the location. I just thought about doing it right now, and it doesn't work as good over the online teaching as it would in the classroom, where you could see me literally pulling my hand away from the board to make a third dimension. Okay, the intersection of 2 lines or line segments forms an angle. So let's say we have a line segment here. And then let's say we have a line segment here. This is an angle. A lot of times we call that angle theta. You could call it X. You could also do it with a ray. So a ray is a line that has a starting point, but then it goes on forever. So this is also an angle. And a lot of times what you guys will see is, for me, when I want to use the word angle, I'll just do like this little, looks like a little compass. The one that you use, you put a pencil in and use it to draw a circle. That's what I often describe or shorthand for writing an angle. The point of intersection is called the vertex. Okay, so this location right here and right here, that is the vertex of the angle. Okay, now you could also do something like this, where you have this. So you have a line here, and then you put a line segment here, or a ray right there. And now from here to here is some angle, but also from here to here is another angle, but also from here to here is an angle. So there's a lot of ways you can think about it. Let's call this theta 1, let's call this theta 2, and let's call this theta 3. It just depends on what they're asking for that particular problem. But all of those are technically angles. You just have to figure out which one they're looking for. Okay, so we have types of angles. We have a 90-degree angle. This is called a right angle. And these are extremely important in basically in society. Think of all the buildings, they're all built on right angles, or a vast majority of them are built on right angles. All of trigonometry, I shouldn't say all, but trigonometry itself is based on the idea of right triangles. So that would be a triangle that has a right angle. And a lot of times we use this little box to represent right. So whenever you see 90 degrees, normally on a triangle, they'll put a little box there to signify that it is a right triangle, meaning it has a 90-degree angle in it. A straight angle is basically just this, where literally you have a straight line and that's 180 degrees. So what if you came around all the way? That would be 360. So half of coming around all the way is 180 degrees. Acute angles, again, a lot of this stuff you guys might remember. Acute means less than 90 degrees, and obtuse means that it's between 90 and 180 degrees. Okay. And again, it can't be 90 because then it would be a right angle, and it can't be 180 because then it would be a straight angle. Okay. So it's between 90 and 180, which makes it obtuse. Okay, find the degree measure of the angles that subtend span a semicircle. So let's do this over here. Let's do part A over here. So let's draw a semicircle. Oops. So that would be 180 degrees, right? Because we go, that's a straight angle. So now let's do part B. Let's do a quarter of a circle. So that would be what? Just this right here, that section. So that would be a right angle. And this would be a straight angle. Okay, and let's do part C, an eighth of a circle. So try to imagine, let's see, if you cut a circle into eighths, probably something like this, right? And that would be an acute angle. Okay, now how do we find, oops, sorry, this is 90 degrees. Now, how do we find what an acute angle would be if it's an eighth of a circle? So we have to go and think about this. So if we have a circle, okay, all the way around the circle is 180 degrees, right? So, I'm sorry, 360 degrees. So what I'm going to do is I'm going to take 360 degrees and I'm going to divide it by 8 because they said it's an eighth of a circle. So we say 8 goes into 36 4 times, right? So that would be what, 45 degrees, okay? So this would be a 45-degree angle. So that's right about here, okay? So this angle would be 45 degrees. 100th of a circle, okay? So that's going to be a very small angle. We can't almost even see it, right? This is also going to be acute. But we would take, and once again, we would do 360 degrees divided by 100, and that would give us 3.6 degrees. Okay, so that's how you can do it, depending on how they want to talk to you about it. That's how you can, how do I say this? How you can calculate how much of the circle you have is you think of a circle in terms of 360 degrees, and then whatever part of the circle they want, you divide it by it. Okay. All right, so let's talk about plane geometry. Plane geometry is the geometry of two-dimensional objects, circles. All points on a circle are located at the same distance, the radius from the circle center. The diameter of a circle is twice the radius it passes through. And I think many people are very familiar with this. So if you drew a circle, right, the way you know that it's a circle is if I draw a line from here to here, or from here to here, or from here to here, or from here to here, anywhere on the end of the circle, or the circle itself to the center should be the same distance. Now, my drawing, according to my drawing, maybe it's not, but it's supposed to be. I just can't draw perfect. So they say from here to here, it should be the same. From here to here, it should be the same. From here to here, it should be the same distance. Now, the diameter is this distance here. So once again, you see how they have from here to here. So any point on the circle through the center to the other side of the circle, right? So if I do right here, that's the diameter. If I do right here, that's the diameter. If I do right here, that's the diameter. Okay, so anywhere that goes through the center from one side of the circle to the other, that is the diameter, which is going to be twice the radius. So whatever the radius is, you double it and you get diameter. Whatever the diameter is, if you divide it by 2, you would get the radius. So it really depends on what problem you're working with, what you want to, what they ask for, and whether you have to double it or half it to get, the radius or the diameter. So a polygon is any closed shape in the plane made from straight line segments. So a regular polygon is a polygon in which all the sides have the same length. So this is something kind of you guys want to focus on. I think in the homework, there's going to be a few questions about regular polygons. So what it means is if you say you have a hexagon, or let's say an octagon, for example. Okay, so if this were a regular octagon, not an octagon, pentagon, I'm sorry. So if this were a regular pentagon, okay, so you see right here, they have that. That means that if I told you that this had a side length of 5, you could then fill in and say, this is 5, this is 5, and this is 5. So that's what it means to be regular. A regular polygon is all the side lengths are the same. Okay, so by them mentioning the word regular, it actually carries weight. So let's say that this side was 2, then that means this side is 2, 2, 2, and 2. Let's say this was a 3, then this is 3, 3. So you guys get the idea. The moment they say regular, it now means that all the side lengths are the same. So you can use that to help you kind of decide how to work with a particular problem. Okay. So I may ask you, find the perimeter of a regular pentagon with one side length of 5. So if I said find the perimeter, okay, and then all I gave you was that the one side is worth, let's not say 5. Let's say one side is worth 6. Okay, well then that means the good news is I know there's 5 sides because of the fact that the shape is a pentagon, penta meaning 5. So that means I'm just going to do 5 times 6 equals 30. That equals the perimeter. I'll just put P for perimeter. Okay, oops. Okay, so it has a perimeter of 30, whether it's 30 feet, 30 inches, we don't know. They didn't really, I didn't really say, but again, you can find perimeter of any regular object just by them giving you one side of it, okay? Triangles are among the most important of all polygons, and they take many different forms. All 3 sides of an equivalent triangle have equal length, making it a regular polygon. An isosceles triangle, by the way, if it's a regular polygon, it's also called an equilateral or equiangular triangle. I think I said that wrong. All 3 sides of an equilateral triangle have equal lengths, making it regular polygon. So if they call it an equilateral triangle, what that really is it's a regular triangle. Or if they call it a equiangular, that's also the same thing. Okay. An isosceles triangle has exactly 2 side lengths that are equal, but then the third is different. And then a right triangle contains 1 right angle. So this is the one we love in math, the right triangles, because they're so easy to work with. We work with a little bit of equilateral and isosceles, but most often in math, we love to work with right triangles because we know so much about them. We know how they work. We know how they behave. The Pythagorean theorem comes up. So we really like working with that. By sketching some triangles, particularly triangles with 1 very large angle and 2 very small angles, you can probably convince yourself that all of the triangles have the following property. The sum of 3 angle measures is always 180 degrees. So no matter what triangle you use, let's say I do this, right? That's not a right triangle. Let's say that this is, 40. Let's say this is 30. Well, then I know this has to be 120 degrees. Oops, 110, sorry. Let me see here. I know this has to be 110 degrees. Okay. So if I give you 2 angles of a triangle, you always can find the third in Euclidean geometry, because in Euclidean geometry, all the 3 angles have to add up to 180 in a triangle. So this is a very important little fact that we should know. Let me see how much we have left. Okay, not too much, but still quite a bit. Okay, let's see here. Let me go back. All right, so it says perimeter and area. The perimeter of a plane object is simply the length. So I just talked about this in the previous problem. Is simply the length of its boundary. We can find the perimeter of a polygon by adding the lengths of the individual edges. And remember, if it's a regular polygon, that makes it really nice for us. The perimeter of a circle is called the circumference. So remember, circumference is the same thing as perimeter, but because circles are special, they have their own special name for perimeter. We can find the area of many geometrical objects with fairly simple formulas. So here's some of the formulas that we have. And the ones that you guys really should know for the rest of your life are pi r squared. You should know, length times width. These are parallelogram, not as often, but technically it's the same as the rectangle. The only problem with the parallelogram is they don't normally give you the heights, so you have to calculate it by using whether it's Pythagorean theorem or something like that. So normally the height is what causes a problem with the parallelogram. And then the triangle. So these are all like core basic ones that everybody should know. If you don't know them, that's okay. Just kind of memorize them. Whether I was a math teacher or not, I would know these formulas. These are formulas for objects that are in our everyday life. You often have to deal with circles, rectangles, or triangles, whether it's in a building. If you ever have to, think about how many square feet you're going to paint something. If you ever have to think about how much carpet you need, if you ever have to build a fence, there's just so many things that, knowing shapes. I remember one time we had to calculate, how much sod we needed to buy for our grass in our front yard, based on, the square footage. So a lot of this, or if it was circular yard, or if it's a rectangular yard, these are all things you have to come up with often. So it says a window consists of a 4 foot by 6 foot rectangle capped by a semicircle. How much trim should be needed to go around? So we need to find the perimeter. So not only do we need to know the window, the rectangle part, but we also need to know this distance here on top. Okay, so what I'm going to do is I'm going to break this into two shapes. So we have this shape, and then we also have the rectangular window. Okay, oops. Okay, so we have the rectangle. Now we know the rectangular window has 4 feet by 6 feet. Okay, now perimeter for this rectangle would be 2 times 4. Well, I'll write out the formula first. It'll be 2L plus 2W. Now that's kind of a problem. Okay, so this is the normal formula. So then I would say perimeter equals 2 L's. So 2 times 4 plus 2 times 6. So this would be 8 plus 12 is 20. So we would want to say that for this particular part of the window, not the top half, we'd want to say it's 20. However, do you notice that we go around the shape, right? We don't go through it right there, okay? So that means that I actually have to erase this piece. I'm not actually able to count that. So then even though it's 20 feet, I actually now have to subtract off this distance, right? This distance would have been 4 feet. So I'm missing that piece. So I'm going to do 20 minus 4 equals 16 feet. Oops. So there's actually only 16 feet that is needed to go from here to here to here. And you could have just added it, right? You could have just said, well, that's 6 and that's 6. That's 12 plus 4 is 16. So that would also work. I just wanted to show you guys, that the formula still works, but you have to adjust for it. Now we notice that for a circle, the distance around a circle is circumference equals 2 times pi times r, where pi is just 3.14 approximately. So we're going to say, well, this is equal to 2 times pi. Now, what's the radius? Now, the radius is this distance here, right? That distance there is the diameter, okay? So we have, well, actually, let me see if we can use their formula. I bet you they use pi times d. So if you're given the diameter, you can use pi times d. If you're given the radius, you can use 2 pi r. Since we were given the diameter, let me come back here real quick. Let me draw the circle. Okay, so we know we only have this circle here. We only have the top half, right? So what I'm going to do is I'm going to find the perimeter of the whole circle, and I'm going to use the pi times d formula. since they gave us the diameter. We know that this is 4, right? Because this is the distance across, and that has to match this distance over here. So we know that's 4. So I'm going to do pi times d, which is 4. So we just get 4 pi. Okay. So let me double check. Do they say? They don't say how they want the window. Let's use 3.14 for pi. Okay. So now we're going to do 4 pi. However, remember, we don't actually have the bottom half. We only have this top half of the window. So we only calculate half of it. So I have to take the circumference divided by 2 because this is a semicircle. So then that means that our semicircle has a circumference equal to 2 pi. Okay, so what I'm going to do is I'm going to come over here and I'm going to do semicircle plus rectangle equals perimeter. So perimeter equals, now the semicircle has 2 times 3.14. That's kind of the common value we use for pi. Even though pi is an irrational number, it's a never-ending, non-terminating decimal that doesn't repeat itself. We approximate it to be 3.14 plus 16. Okay, so now let's see what we get. That'd be 6.28 plus 116, so that'd be what, 22.28 equals P. And we could round this off to 22.3 feet equals the perimeter. And that's what we could call our perimeter for this particular problem. Okay, maybe I should do this 20. So I'm going to do 20 minus 4 is equal to 16 feet. That is the erasing part that I did right there. Okay, so we get 22.3 feet. All right, let's look at building stairs. You have built a stairway in a new piece, in a new house, and want to cover the space beneath the stairs with plywood. What area of this region? What is the area of this region? So we need to find this area right here, you guys. Okay. They want to cover that with plywood. Well, that's a right triangle, right? Because it's built, its stairway is built on a right angle. So I'm just going to take this triangle and I'm going to kind of take it off over here on the side. And we know it's right. We know the height is 9. And we know the base is 12 feet. Okay. So now what I need to do is I need an area formula because I need to know what size of plywood. I don't need the distance. I don't need the perimeter of the plywood. I need the area that it's going to cover up. So what is the area of this region? So we know that area is equal to 1/2 base times height when it comes to triangles. So that means that area equals 1/2 the base, which is 12, times the height, which is 9. So this will become what, 54 feet squared. And in general, when you're doing square footage, you do this little symbol right here, feet squared. That's how you say square feet or square yards or whatever you're working with. Okay. So hopefully this will help you guys a little bit with some of the homework problems. Two of the most important properties of three-dimensional objects, such as a box or a sphere, are its volume and its surface area. So now let's look at some formulas for these. And again, you guys, this is just kind of common formulas that you can use. And it's more important right now at this point in the course that you know them so you can plug stuff in. It's not a test on memorization, but you know, if you know how to use them, that's what's important. Okay. So sphere is 4 pi r squared for the surface area. And understand when they say surface area, they mean like, imagine if you had to wrap it with paper, like if you were wrapping a Christmas present, how much paper would it take to cover that? Okay. Not how much liquid could it hold or how much, you know, sand or whatever you can put in a box, but how much paper would it take to wrap a present? That's when they talk about surface area. When they're talking about volume, they're saying how much liquid could you put in there? How much can it hold in terms of, you know, how much dirt or whatever? How much can it hold basically is its volume. Okay. So a water reservoir has a rectangular base that measures, so let's draw a water reservoir, has a rectangular base that measures 30 meters by 40 meters and vertical walls of 15 meters. It was filled to capacity. So let's do this, 30 meters. So I'm not too good at drawing three-dimensional objects, but I'll give it my best shot. So one of my students taught me one time, I think they were in art, you draw it like this, and then you connect this. Okay, so that's our box, okay? And it says that it's 30 by 40, that's the base, and then the walls are 15. So we know that this is 15, this is 15, this is 15, and this back wall is 15 in height, okay? It was filled to capacity. At the end of summer, the water depth was 4 meters. How much water has been used? So they're saying, you got like a water level. It's drained, right? So we've drained the water level to there, okay? So what we need to do is we need to find out how much water it originally holds versus how much water is left now, and then subtract them. And that'll tell you how much water was used. So what we're going to do is we're going to do the formula for a rectangular box or prism. It's for volume, it's length times width times height. So volume of, I'll put for full, equals 30 times 40 times 15. So I'm just going to take out my calculator and I'm going to do 30 times 40 times 15. And that will be 18,000 meters cubed. Okay. Now volume of what's left. Okay. So now here's the thing. They said at the end of the summer, the water depth was 4 meters. So that means it's still 30 times 40, but now it's only 4 meters tall, the water. So we're going to do 30 times 40, but now we're only going to do times 4. And that would be 4,800 meters cubed. Okay. So now we're going to do volume full minus volume left over. And that should equal volume used. These are little subscripts. It's an easy way in math to kind of describe what you're talking about. So let's see, let me do it over here. So volume full would be 18,000 minus volume left, 4,800. And that equals 18,000 minus 4,800. That equals 13,200 meters cubed. Okay, so no big deal. I think we're getting close to almost done. All right. 5 perfect solids. Plato formed ideas about geometry in the universe involving 5 perfect solids shown below: the tetrahedron, the cube, the octahedron, the dodecahedron. I've never heard of that one. And then the isosahedron. So these two I've never really heard about. These I've heard about, and especially the cube and this one. Okay. So each of the perfect solids is such that all of its faces are the same regular polygon. Okay. So basically they're saying that when you put all these faces together, they're the same exact shape. So this one has the same size face as this face, and this face is the same as this face, or this face is the same as this face, meaning they all have the same, they're the same polygon. They're perfect. We're not going to go too much into that. Scaling laws: length scale with the scale factor, area scale with the square of the scale factor, and volume scale with the cube of the scale factor. So what you need to do with scaling factor is you need to find out how much it's changing by, and then determine if you're working with length, area, or volume. Okay. I'll kind of show you what that means in this one. Suppose that magically your size suddenly doubled. That is, your height, width, and depth doubled. For example, if you were 5 feet tall before, you are now 10 feet tall. By what factor has your waist size increased? Okay, so let's think about that a second. Let me turn my page in my notes real quick. So if you think about your waist size, okay, you know how like what you see in like TV shows, oh, this is the end. Okay. So you know how in TV shows we see that, let's call this part A. I don't want to do it in red. They'll have like, they'll take somebody to the, for a wedding or something like that, and they have them sized, and they'll measure, and you'll see a person with like this tape measure for tailors, and they measure the distance, how long your pants are going to be, how much your dress is. Well, they also measure around your waist. They wrap it around you and they say, okay, this is your pant size or whatever. Well, that is a distance around something. So literally, that's perimeter, okay? So that means that your waist size increased by perimeter. So this is perimeter. Okay. And let me see. So perimeter, by what factor has your waist size increased? So your waist size has increased. So perimeter, since it's perimeter, we double the scaling. So right here, look up here, it says length scale with the scale factor. So I'm sorry, we double your waist size. Okay, so let's say that the scaling, and so the scaling factor is 2, right? So that means, let's say your waist used to be 30 inches, okay? It would now become 60 inches. So that's what they're saying here, is when they say length scale with the scale factor. So whatever the scale factor is, you just multiply that. And the reason for that is when you calculate length times width, well, what if they both changed? Well, let's say you doubled your length and you doubled your width. Well, then wouldn't that technically be 2 squared because there's an extra 2 in there? But when you're just doing lengths, it's no big deal. You just use the scaling factor as it is. Okay, so let's look at part B. Part B says how much more material will be required for your clothes. Now that's surface area, right? So that's area, all right? And so that's not volume, that's not length. That's how much like actual material would be used for your shirt if you became, double in size. So that means this is area. And that means that we are going to square the scaling factor. Okay. So let's say originally you needed, I don't know, I'm just going to make this up, guys. I don't actually know if this is correct. Let's say you needed 150 inches squared of material for your shirt. That sounds like way too much. Let's do something smaller. Let's say you needed 40 inches squared for material. That's still way too much, but who cares? 40 inches squared for your shirt. Then let's say that you want to know for your new shirt how much you're going to need. Well, we would do 40 times 2 squared. Oops. 40 times 2 squared, because whatever the scaling factor is, we have to square it. So now we would need 320 inches squared. Okay, because the scaling factor was 2. The scaling factor was 2. So then because it was area, it says up here, you have to square the scale factor. So they said double, right? You're going to double in size. So then we are going to square that doubling. And that gives us times 4. And 4, what am I doing? That's not 320. What am I thinking? 40 times 4 is 160 inches squared. Okay. I don't know why I did 8. I think I did 2 cubed in my head or something like that. Okay. So then for part C, it says by what factor is your weight changed? Okay. So weight is volume. Okay. I think that's what they mean by weight. That's your volume. So then we have to cube the scaling factor. Okay, so let's say that your weight, wow. Okay, so let's say I weigh 285 pounds, which I do. So I'm 285 pounds. And if I doubled in size, that means that I would have to take 285 times 2 cubed, right? Because the scaling factor, once again, is 2. And that means I have to cube it, right? So they say right here, cube the scale factor, okay? So that means I have to do 285 times 8, because 2 cubed is 8. So then that would give us 2,280 pounds. So that would be my weight if I doubled in size. So that's actually a massive increase. If you think about it, that's what, 10 times, I'm basically not quite 10 times, 9 times bigger, something like that, in terms of volume. So yeah, it's crazy how much it would go up. If you doubled in size, your volume would change a lot. Okay, you guys, so I think that's it for this video. Just a little bit of information here at the end that you actually had to do some calculations. But in general, most of this section was just information. And then I think in the homework, they're gonna ask you to do like these type of calculations here, answer a few questions, and then do these type of calculations. So just keep an eye out for that. Thanks for watching the video, and I will see you in class.